out and I haven't yet described properly is like, as I mentioned before, that we'll make a split if we can find like a group of samples that are pure. Thing is how to define that group of samples are pure. One way is to look at what we call information gain for classification and variance reduction for regression. But let me describe this in the regression first, because I think it's simpler to understand. Let's say when you have a decision node that is your parents' nodes, and you know that this parents' node will have two child. What is the best splitting for the child? The best splitting, okay, let's say if there's some pink here, the best splitting is the splitting in which you are able to get pure group of samples. And actually, if you measure the error at the parents first, let's say if you measure the variance of the parents, that is you use all these training samples, like all the y, and compute like a square error with respect to the mean. So probably at this stage where you compute the variance for your parents, this variance will be quite high because your data samples are somewhat, like it is like you collecting various types of samples together. So your variance will not be low. However, if you can find a split, for example, this pink curve, maybe I should change the color. Okay. Let's say if I can get a split, let's say this purple curve, then if this split is good, then I will be able to have a split that gives me like a lot of reduction from the parents' variance. For example, if I get this splitting, that means that the variance belongs to these child nodes, like the pure set of samples. It will be having a very low variance, nearly zero, right? So now, if you have something like very low like that means your partitioning is good because you're able to separate like a pure set of samples out of the mixed one. And actually the one on the right here is still somewhat mixed, but it's probably not as bad as if you were combining all of them together. So when you compare the weight sum of your child for your first one that is nearly zero, and that one that is probably higher, but not much higher than your parents, then that means you will get some kind of variance reduction that is significant enough. So if you have variance reduction that is significant enough, or maybe compared to other partitioning, for example, if I make a partitioning that kind of look like this, that means my first variance and my second variance are somewhat at the same level. And if we combine, it's probably not that different that if you were to combine every point. So that means in this case, the variance reduction is not good. You should not split here. So that is how we find the best splitting. And actually the definition of having pure node or maybe like a pure samples is like when you're able to find a group of samples that give you the lowest variance possible. So that is when you're able to cut down the variance from your parent node, or maybe from before that you do the splitting. So that is the key idea. Another one that we have to talk about is, what about classification, right? In here, it's actually very simple as we look at the regression task. We are able to compute the variance. It's kind of like not very far from our idea, but okay, in this one, you have to bear with me a little bit. I'll try my best. In this one, when we compute the parents, actually the idea is the same for entropy and Gini index. But let's say I'll talk about entropy. Just know that it has the same tendency. Okay, for the parents, if you compute the entropy of points that is like this, actually it's like a point where you have, it's like a node where you have samples that are mixed between two classes. Therefore, very likely, if you compute the probability of maybe being in class pink, this probability is probably about 0.5. It's going to be 0.5. If you remember that entropy graph, 0.5 is actually a very high entropy. Meanwhile, if you're able to split them, you get this one. Let's say this probability is probably very high on the pink class, nearly equal to 1, and very low on the black class. So that means this entropy will be much lower than before. Sorry, entropy for 1 and 0 is actually equal to 0. If you have 0 and 1 here, so you have a very low entropy. But this one, when you have a mixture again, it will kind of go back to that previous case again, where you have a mixture of class. Therefore, your probability will be somewhere like maybe 0.4, 0.5, 0.6. Those will have high entropy again. But definitely it shouldn't be higher than if you collect all of them together. So if you have like a high differences between your parents and your child, some of your child, then that means you have high information gain. So you can think of this as high information gain, this is high variance, then you think of it as that actually indicate a good splitting. Or you can imagine that two of these indicators are saying that if you are able to find a group of some samples that are pure, the value will be low. So it will create some high differences with the parents. Below here is like example of how we maybe use Gini index or maybe entropy for finding information gain. For example, if you have two thresholding values, for your first one, as you are not able to separate them, you probably have some, low information gain. But if you can find the group of samples that are purely or clearly divide the samples that is of a certain class from the other, then very likely you will have a high reduction because this one will go to 0. And if you have 0.5 minus some 0 value, yes, of course you will have some high distinction. This is for information gain. And for the variance, it's the same. Because if you are able to group these sample points that belong to the same class together, maybe this group or that group together, very likely your variance will approach 0. So it's kind of like same idea for the two cases. So maybe can I have some 5 minutes break because it's actually already the end. Yeah, but okay, before the end, let's talk about the advantages and disadvantages of the tree-based algorithm. So firstly, it is good because you have the graphically displayed how it makes decision. And you can actually apply the tree on your input feature directly without doing any normalization because it's performed some kind of thresholding. You don't need to normalize them. So that's a good thing. But the bad thing is that it's very unstable because as we see, the way we do the partitioning, the thresholding, it depends on the distribution of your training samples. So it can be very sensitive to any small changes in your training data. And usually, if you have, let's say, multiple nodes in a tree, let's say you have so many decision after decision after decision, that means your tree is going to be a very long tree. That long tree will tend to have high variance and lower bias. And what this means is that it will tend to overfit to your training. Just like if you have made so many decisions based on a training samples, so that means whatever you get here is going to be very well fit for your training data, but usually the problem will be it will be unlikely to fit your testing. So that's what we say it can have the overfitting problem. And actually this problem will motivate the next chapter as to those techniques that we will talk about will be the one that is employed to fix this particular problem. As we know, tree with a short width, let's say if you only have a single decision making, that means that this tree is very likely biased by whatever you see in your training, and it probably won't capture anything at all about your testing. So yes, it will have a problem of underfitting. But usually when you use tree, we will very likely get your first case than your second one. Because with your data sample, you can always sort, split, make a decision again, sorting, splitting, make a decision again. It tends to go on and on than having a very short tree. Yes, and lastly, it tends to have higher variance than any linear regression. As for example, in this example, that if you are able to separating your data with this, let's say, hyperplane, right? If you have a linear regression, you can probably track that separation. Or maybe if you have, let's say, the nonlinear regression, like a sigmoid function, you can separate them. But if you do the tree, thing is the tree decision tree will probably give you some kind of splitting that look like this. Even though at the end it can do some kind of do some kind of binary classification, but the thing is it will come up with some gap here, like here, here, here. That is not necessarily there, but it's there because you are making some kind of hard decision making, like the thresholding value. Meanwhile, on the other hand, if your data is somewhat non-linearly separable, like that, you may be able to use some support vector machine to separate them, but linear regression or any sigmoid function wouldn't perform well because your decision making is highly non-linear. On the other hand, your decision tree may perform well because once you find the thresholding value, then it cuts, then you can somehow imitate this decision making. Yes, so that's it. For this lecture, we will go to lecture 14 about, let's have 15 minutes break.